Hello folks, this is 2024 October-November paper 4-2 and the question number is 2. This question is concerned with the chapter gravitation and it has a tint of the chapter cosmology as well, the last chapter. So it says that the sun may be considered as a uniform sphere with a mass of this much. So this is the mass em here, and a surface temperature of this much. This is the temperature T. A probe with a mass of this much, which is a small m, moves in a straight line towards the sun. When it is a distance of x from the center of the sun, so it means the sun is over here, this point is here, the distance is from the center. So this is the distance, this is x here, x. The probe measures the gravitational field strength z due to the sun and the radiant flux intensity F of radiation. So F here is not the force, it is the radiant flux intensity. The first question is define gravitational field. So it is the force experienced per unit mass in the field of influence there. So next question is for the position of the probe where x equal to this much, calculate g. So we should have this g is equal to gm by x square. Since the distance is x, I must use x square here, which gives me, or g is equal to, the large g is 6.67 into 10 to the power minus 11 into the mass is 1.99 into 10 to the power 30, and this x is given as 1.47 into 10 to the power 11 and then squared. So it should be equal to, if it's calculated here, 6.67 exponent to minus 11 into 1.99 exponent 30 divided 1.47 exponent 11 squared equal to, so this becomes 6.14248 and so on into 10 to the power minus 3. So when I write it in 2 or 3 SF, it is 6.14 into 10 to the power minus 3 Newton per kg. Then determine the gravitational potential energy EP of the probe. So this its formula will be equal to EP is equal to minus gmm by this x. So that's equal to minus 6.67 into 10 to the power minus 11 into 1.99 into 10 to the power 30 into this small mass is 2.63, then whole divided by this x is this much 1.47 into 10 to the power 11. So this will be so 6.67 exponent to minus 11 into 1.99 exponent 30 into 2.63 divided 1.47 exponent 11 equal to, so it is a large value here, so it is a 2.3747 etc into 10 to the power 1 2 3 4 5 6 7 8 9, so it is 9. So this will be 2.37 into 10 to the power 9 joules. Now show that for any particular value of x, the numerical values of z and f are related as. So the first thing is we have z is equal to gm by x squared, which gives us x squared equal to gm by z. Again we have L is equal to f is equal to L by 4 pi x squared, which gives us x squared is equal to L by 4 pi f. So one is x squared equal to gm by g, the next is x squared equal to L by this much. So when I match these two, I will have L by 4 pi f is equal to gm by z, which gives me z is equal to gm into 4 pi f by L. This will give me, when I arrange things, it will be 4 pi gm by L then f. then F. So this is the value of G and as required by the question. Now figure 2.1 shows the variation of G along with the graph. So it shows the variation of G with the F in a graph. Let me fix this. Yeah, now it works, I suppose. So the equation is here and the graph is here. So according to this graph, we have F in the x-axis, Z in the y-axis, and this is the slope, which is M. And the graph should be a straight line through the origin. Yes, it goes to the origin. So here, determine a value for luminosity L of the sun from this graph, and we have to give a unit. Now what happens here is, from this graph, let us first find the slope. Slope is equal to M. So M is equal to y2 minus y1 by x2 minus x1 equal to, so y2 here is this point, let me see this point. So this point is, if this is 4, this is 6, this should be 6. So if this is 6 and 8 here, there are 5 divisions, so it should be 6.4, 6.8, 7.6. So it is 7.6 minus 0 into 10 to the power minus 3 whole divided. Then here it is 1.5, 2 in the middle, it is 1.75. 1.75 minus 0 into 10 to the power 3. So this should be equal to 7.6 exponent minus 3 divided 1.75 exponent 3 equal to like this. So it is sorry, I have made a mistake here. It is 1.75, yes, equal to. So this becomes 4.34 into 10 to the power minus 6. This is the value of the slope. Now the slope is equal to this much. So I have slope is equal to 4 pi gm by L, which gives me L is equal to 4 pi gm by L goes here, slope goes here, slope. So this should be equal to 4 pi into Z is 6.67 into 10 to the power minus 11 into mass was 1.99 into 10 to the power, let me refresh myself, I forgot the value, 30, 10 to the power 30. 10 to the power 30 whole divided this L. So this L is 4.34 into 10 to the power minus 6. So this will be, so this thing is in the denominator. So we have 4 into shift pi into 6.67 exponent minus 11 into 1.99 exponent 30 divided the answer equal to, so this becomes 3.84 and lots of quantities into 10 to the power 26. So I have 3.84 into 10 to the power 26 and the unit is watt. So its unit is watt. Now use your answer in C2 to determine the radius r of the sun. So we have the Stephen Boltzmann law. L is equal to 4 pi sigma r squared t power 4. Stephen Boltzmann law. This is a very revolutionary law. So this gives us we need to find r. So it is r squared equal to L by 4 pi sigma t4 and r is equal to L by 4 pi sigma t4 power 1 by 2. So this gives you r equal to bracket L is this 3.84 into 10 to the power 26 whole divided 4 pi into the value of sigma is 5.67 into 10 to the power minus 8 into T is the value of temperature is 5780. So it is 5780 power 4 and then it is power 1 by 2. So this will give me And give me, so this is 26 divided 4 into shift pi into 5.67 exponent minus 8 into 5780 power 4 bracket close equal to, and again it's power 0.5, root means power 0.5 equal to, so this becomes 6.9495 and so on into 10 to the powers. So it should be 1 2 3 4 5 6 7 8, so 8 meters. So it should be 6.9595 into 10 to the power 8 meters. So this is the answer to this question.